Fourth example, final example, the radioactive isotope uranium-237 has a half-life of 6.75 days. Now what's half-life? We'd have to go figure that out. Luckily they gave it to us right here. Half-life is the time it takes for 1/2 of the isotope, 1/2 of the material of our isotope, to decay and break down, to go through a process of decay. If you start with 1 kilogram of U-237, how much will have not decayed after a year? So we're saying after 6.75 days, we will have half a kilogram, right? We start with 1 kilogram, and we know after every 6.75 days, we will have lost half of our starting material. So we'll be down from 1 kilogram to half a kilogram that has not decayed. So let's see if we can figure out a way to turn this into another function. So let's make it amount. The amount of our isotope that is not decayed based on time is equal to, how much did we start with? We started with 1 kilogram times what happens every cycle? 1/2. We half it every time we hit it on a cycle. So we have every time we hit on a cycle. So how fast is a cycle? Number of days, we'll make t into the number of days, because we see that we're dealing with days based here. So t divided by 6.75. So let's do a real quick check. So we check because we know after 6.75 days, we should have 1/2 a kilogram. So let's check that by plugging it in. A of 6.75 is going to be 1 times 1/2 raised to the 6.75 over 6.75, which is the same thing as just 1/2 to the 1, which equals 1/2. So sure enough, it checks out. Seems like the way we've set this up, seems like it passes muster, because it's going to divide by half every time the 6.75. So if we plugged in double 6.75, it would divide by half twice, because it'd be 1/2 squared. So seems to make sense. We've set it up well. And we can see that this also can we just write as 1/2 times, well, let's just leave it as it is. It gives us a better idea of how this works in general for half-life breakdowns. So now we're going to ask ourselves, how long? What is the time that we're dealing with? In our case, t is 1 year. What is 1 year in days? Because we set up our units as days, because that's what our half-life was given to us in. So 1 year is 365 days. So at the end of that, when you plug in 365 equals 1, the amount that we started with, times the half-life will occur every 6.75 days, and we're having 365 days go in. We plug that all into a calculator, and we get the amazing number, amazingly tiny number of 5.273 times 10 to the negative 17th kilograms. Really, really, really small number. To appreciate how small that is, let's try to expand it a bit more. So kilograms is 1,000 grams. Sorry, 1 kilogram is 1,000 grams. So that means that a kilogram is 10 to the third grams. So we could also write this as 5.273 times 10. If it's 1,000 grams for a kilogram, then that means we're going to get to increase by 3 in our scientific exponent. So scientific notation, we're now at 5.273 times 10 to the negative 14th grams of our material, which if we wanted to write this whole thing out, we would be able to write it as 0.00000, 5 so far, 0.00000, 10 so far, 0.00013. And let's see why that's the case. We can stop writing there, because if we were to bring that 10 to the negative 7, taking to the negative 14th here, and remember it's in grams because we had grams here, because that would count as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, because we can move the decimal places 14 times to the right by having 10 to the negative 14th, and that's how that scientific notation there is working. Or alternatively, we could also write this with kilograms as the incredibly tiny 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 5.273 kilograms. And if we counted that one out as well, we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So we've got that 5.273 times 10 to the negative 17th kilograms there as well. So it's much easier to write it with scientific notation. That's also probably what a calculator would spit out, because it's hard to write a number like this long on a calculator. So we're much more likely to get it to see it in scientific notation. So 5.273 times 10 to the negative 17th kilograms, which is absolutely minuscule amount of radioactive material left, considering that we started at 1 kilogram. So that shows us how decay works. All right, cool. We've got a pretty good base in exponential functions. Next, we'll see logarithms and see how logarithms allow us to flip this idea of exponentiation. And then in a little while, we'll see how logarithms and exponential functions, how we can sort of oppose the two against each other. Pretty cool. We can find out a lot of stuff with this. All right, we'll see you at Educator.com later. Bye.